Okay, let's look at another example of using force diagrams to compute accelerations, and this is going to be from number 32 in chapter 5. And this problem says that you've got two children that are pushing horizontally on another child that's inside of a wagon. And one of the children is exerting a force of 75 newtons, the other is exerting a force of 90 newtons, and there's friction of 12 newtons. And then it gives you the mass of the child plus the wagon. It asks you to figure out what the acceleration is of the child in the wagon. Okay, so I'm going to go ahead and first of all, our strategy for solving this problem is we want to look at, we want to identify the system that we're interested in, and we want to use free body diagrams. Okay, so first of all, to identify the system, I'm just going to draw a picture of what's going on. So here's the surface. We have one child standing on the left-hand side, and they're pushing that direction. Got the cart in the middle with another child inside. And we have someone on this side pushing in the opposite direction, standing on the surface like that. And the question is, we also know there's friction, but we've got to figure out which way this is going to move first. There's friction in here, and the question is, what is the acceleration? So first of all, identifying the system of interest. The system of interest, all we care about is the motion of the child and the wagon. So we don't care about the force of the feet on the surface of the earth, and we don't care about the gravity of the two children on either side, or their normal forces or anything like that. So what we care about is this child right here. So that's going to be our system. This is going to be the child and wagon. So that's where we're going to put kind of our dot that represents the point that we want, the point of the system where we want to figure out what's moving. Now that we have the system identified, we can start to identify the forces that are acting on this. Let's write down things that we know now. We know that the let's put it says the first child is pushing with 75 newtons. The second child is pushing with 90 newtons, and there's a frictional force of 12 newtons. Okay, so we're going to have force in one direction is going to be overcoming friction and the force of the child pushing in the opposite direction. The other things we know is the mass of the cart and the small child in the cart is 23 kilograms. So we know that. And I think that's it. Okay, so now let's look at our solution. So for a solution, the first thing I'm going to do is draw my free body diagram. So here is my system, the child in the cart, and things I know is I know their gravity, so I'm going to write that down. That's their weight. That's equal to m times g. We also know that there's an equal and opposite normal force, Newton's third law, pointing up. We'll call that the normal force. And then if we have the first child pushing from, first of all, let's decide who's first and who's second and what direction this would move. So let's say that the direction that this thing is going to move is to the right. Just so we have a positive acceleration. So if it's moving to the right, that means our frictional force opposes the direction of motion, because that's trying to slow us down. So I'm going to put my frictional force there, and that means that the child with the stronger force needs to be pushing to the right. So we're going to call that F right. We'll call that 90 newtons. And then we call the force from the child on the left pushes this way, or sorry, the force to the left pushes that way. We'll call that force left, and that's 75 newtons. Okay. So that gives us an idea of what our free body diagram looks like. So, and we know that the force of friction is 12 newtons. So that tells me that 75 plus 12 should be less than 90, and that will result in a force that's pushing the child to the right. So let's go ahead and write down our components. So there's our free body diagram. Then we do our components. Now in the components here, we don't care about that y direction because the normal is equal to the mass, and that's all given there. So we're not going to worry about that, but we do worry about the x direction. So we do the sum of the forces. We have minus 75 newtons. Well, let's go ahead and write these in algebraic form first. So we have minus the force to the left, because it's going that direction. We have minus the frictional force, because it's going in that direction. Then we have plus the force to the right, it's going in that direction, and that all has to equal mass times acceleration in the x direction, which should be positive. And now we can go and put in the numerical values for this. We're going to go ahead and divide through by the mass. So we're going to get minus FL minus F plus FR divided by M, and that's equal to the acceleration in the x direction. So that means the acceleration in the x direction is equal to minus 75 minus 12 plus 90 over M. And that is the same as, well, let's see, 75 and 12 is 87. So 87 plus 90 is 3 newtons divided by the mass in kilograms, which is 23 kilograms. And that's going to be equal to, that's going to be something like 0.15 meters per second. Because 3 halves is 1.5, and then we have an extra factor of 10. And I just rounded this to 20 to make the math easy. Meters per second squared. Okay, so that gives me my acceleration. And does that make sense? Well, you could ask yourself, if I move for 1 second, how far would it go? If that means if they're pushing and there's friction and they push with this relatively small force, if you go for 1 second, it would move about 15 centimeters. And that seems order of magnitude to make sense here. So for my significance, I could say order of magnitude looks good, and the units are correct. Units look good. Okay, so again, our strategy here, we draw a picture so that we can figure out our system of interest. That makes it so we don't have to worry about anything but the most important things. We draw our force diagram, which has all of the forces that are acting, friction, gravity, Newton, all of the other forces acting. Then we do our calculation and we check the results to see if that looks good.